This is Cosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen. This is Cosmographia, the Randall Carlson podcast, and this is episode 102. Isn't that right, Brad? Make sure I got the right 102.
Right after 101.
Oh, are you sure?
Yeah, I took a week.
You got a source
studying.
for that? You got a source? So I think Randall's got a bunch of stuff planned to discuss today, and there's also an interesting paper that we'll bring up later on a possible giant solar flare a long time ago. So that has been going around. The headlines have been going around about that.
Curious timing for our younger Dryas and bowling alley rods and
yes,
terminal Pleistocene events.
Yep. So what do you got for us today, Randall? What do you got planned?
I'm supposed to have a plan?
It's all you, man.
What's the lesson plan, teacher?
It's all on me. I can't handle the stress.
Got all those books. Damn. Gotta have something.
Yeah, well, I thought we'd go through one by one my books, and I will do a quick review, quick synopsis of each book.
People have offered to come and categorize everything and make a database, and, I've seen it.
Yeah. Oh, really?
Yeah.
I probably should talk to some of those people.
Yeah.
Who are these people?
Steven got it started, but yeah, I'm sure there's another layer necessary.
There is another layer. It's made a lot of progress, but it's not a finished project yet.
Yeah.
There's still some disorder, things that could be moved around and categorized more effectively, I think. But compared to what it used to be.
You never want too much order. You need a little chaos in there. And then when you have order and chaos together, that's when you get innovation.
That's when you get innovation. I'm totally a believer in that. So you cannot see my workspace here in front of me. So what's happened here, though, is an asymmetrical disorder because try to keep everything kind of that's, within the viewport relatively organized. So what's happened is all of the disorder and disorganization has sort of concentrated on the area that you cannot see.
Yes, that's the same thing in here. So you can determine the camera view by looking at where all the disorder is.
Yeah,
versus
immediately outside the window.
Yeah,
it immediately degenerates into disorder. Right.
That's right. Yeah. So you can walk in the room and be like, this is the part the camera can see. And this is the part it can't see. Yeah.
Yes. So you guys do then understand that principle.
We have been podcasters for a while.
Yeah, we absolutely understand it.
Okay. Well, I mean, several of the things the matter of the sun has been interesting to me. I read you guys a quote about this. I'll call it an essay that I have been writing.
Yeah.
And a lot of the essay is about geopolitics, so I won't get into that. But I kind of opens on that because of the fact that because we're so preoccupied now with conflicts amongst each other, we're not really looking at the bigger picture. And we need to be looking at that bigger picture. And just like the paper that you're going to talk about in a minute, Russ, very much is a reminder of that.
Yes.
In spite of the fact of what we're doing down here within the human scale of things, there's a much bigger reality that we're a part of. And from time to time, with a much greater frequency than we previously realized, that greater reality impinges upon our lesser reality down here on this planet. And to me, probably part of the double concern about all of the shit that's going on so many levels, with whether it's, geopolitics and international relations and conflicts, all the way down to what's happening in academia and all of the things that, the younger generation is now being distracted with. And then on top of that, the whole climate crisis or climate emergency, which is basically all contrived. As we've talked about, I think anybody who watches this podcast regularly knows that there's an enormous amount of evidence that contradicts that narrative. In fact, I might even pull up a recent graph released by National Oceanic and Atmospheric Administration, which shows temperature anomalies in North America over the past few centuries. And it's a very interesting graph. I don't have it at my fingertips right now, but maybe on the break I'll pull it up. But yeah, so that paper, Russ, that you're referring to is new evidence that that supports the possibility of there having been tremendous solar storms, bursts of solar activity that have the potential to affect things here on Earth. My question when I was not aware of the paper, actually. I was not aware of the paper because I just can't be aware of everything that's coming down. And that's why I really appreciate working with you guys, because you guys catch things sometimes that I would otherwise miss. So you presented that paper and you said that the dating. Well, why don't you go ahead and just kind of explicate a little bit? It's based on tree ring studies, which is
that's right.
Dendrochronology.
Right. Dendrochronology. So it was published in the Royal Society's Philosophical Transactions of the Royal Society A. I think they received the paper in 2022, and they've just published it. And basically, the idea is that that people have been a guy named Miyake, I think his name is. Let me make sure I got that right. A Japanese scientist, a physicist, found that in tree ring data in Japan that he was looking at, he was finding very large spikes of C14 in single rings. So quick events, right? And these became known as Miyake events. And then, so these researchers were looking at tree rings from Pleistocene trees. These were late Pleistocene trees, and they have 700 years of data. And they say that it's floating. They are not able to very strongly connect it to Holocene tree ring data yet. But so they're calling it a floating data set, right? But they've basically got good information of what time it's in, and they've tentatively connected it to Holocene tree rings. So at 14,300 BP calibrated, they found an enormous spike of C14 in the tree rings, and these were trees that are washing out of a riverbank in the French Alps. Okay, so they're just stumps. They were growing there in the late Pleistocene, and then they got covered in silts. And so now you've got just stumps. They're still in situ. They're upright, and they're washing out of this riverbank slowly. Every year, a few more of them get exposed, and these guys took samples from a bunch of trees and got a 700-year long. There we go. There's a picture of them. So they were taking samples from these trees, and right at 14.3, they found an enormous spike of C14, and then they went to the data from the Greenland ice cores and found a corresponding spike of beryllium-10, which is another cosmogenic particle generated by cosmic rays, the same way that C14 is. So was the C14 and the beryllium-10, typically they will be produced when the sun goes into a state of inactivity, allowing more galactic cosmic rays to bombard the atmosphere. That's right. So okay, but they're attributing this to what? Intensified solar activity, to a coronal mass ejection, a solar storm? Yes, exactly. Like if an enormous solar flare that directly impacts Earth. Right. Which could cause the spallation of neutrons. Yes. Resulting in the radiogenic byproducts of carbon-14 and beryllium-10. Exactly. And others. Okay. Yeah. That's the idea. Now I was looking through the paper that's published here, and then of course they're referencing the Miyake work. So I'm looking at that. I'm like, where exactly is the strong correlation to solar activity? Maybe it's there, and I'm just, I just can't understand it. But from what I can tell is they're saying this is probably what it is. But I don't know. maybe
so
somebody,
looking at this photograph here now, like you said, they're upright stumps.
Yeah,
that would look like they have been preserved because of the fact that they were entombed in this sediment.
that's right.
And the river has washed it away and finally exposed them. Now, where are the anomalous rings within the lifespan of the tree?
There's a whole spread because they identified 3 different sets of trees, the oldest set, and then there's a mid-range set, and then there's the youngest set. And then they kind of combined them all together, right? And they got a big 700-year span of time.
Okay. So, and now the youngest is dated at 14.3 or the oldest? Or
I couldn't figure that out. The 14.3 is in the range.
Within the range.
Found.
Okay.
Yeah,
So it might be like a median.
Yes. And multiple trees have the rings that have the spike. Some of them it's the oldest ring and some of them it's very young. So
okay, so the trees did continue to live on after they
I don't think
served the fingerprints of this cosmic event.
That's right. I didn't see any indication that the trees were killed by the event. So.
Right.
So
now looking at this photograph, it looks to me like pretty much this is a massive sedimentary deposit, not layered.
Yeah.
Not
well, they did say there were 3 inundations of materials that buried trees.
Okay.
So the oldest trees continued to grow after being partially buried, but they grew much slower. And sometimes didn't form rings at all, which made the dating the map confusing. Because if the bottom of the tree, 6 meters of the bottom of the tree is buried in silts, it doesn't grow as well. Right?
Sure.
Because it's being suffocated.
Well, looking at this sediment here, it's actually, what you'd call a diamict with all of this jumbled stuff in it. And you can see, starting to get some boulder size clasts within the sedimentary layer, which shows that it's probably a very singular event that came in and buried these trees. And then you've got the upper layer here that looks like it would probably be consistent with Holocene soil formation on top of a flood deposit. So, is there a relationship between the flooding events, which of course are indicative of something going on in the climate, and the radiogenic anomalies? That's the question that becomes on my mind. And you said 14.3, which puts it within 300 years of the typical date given for meltwater pulse 1A.
Right. The paper is saying that it's right in the short period between the Balding and the Allerod. There's like 100-year period in between those two geological times.
You took it away, but the 3 layers, it looked like there was a gray layer at the bottom and then equal height of a more stratified layer of sandy, and then that diamic layer on top of it that was probably 3 times as thick.
Exactly. Yeah, I didn't go into that, but you kind of have that buff colored layer on top of the gray layer.
Right.
There's this part in the paper. It says
real quick about meltwater pulse 1A. It's a range of dates because I looked this up when we were talking about this paper. They say, just the first thing that comes up on Wikipedia is that it's a period of rapid post-glacial sea level rise between 13,500 and 14,700. So that this date actually falls right in there.
Right in the middle,
in the middle, yeah.
So what okay, you just read on the meltwater pulse 1A.
Yes, this is just on Wikipedia of what it's they're just saying it's paleoclimatologists and oceanographers use this. This is the name of something that they say is for a period of rapid post-glacial sea level rise between 13,500 and 14,700.
13,000.
Yes.
You said 700.
13,500 and 14,700 calendar years ago.
So that's 1,200 years.
Right.
That they're allowing for Well, that's a little bit different than some of the other studies that would put it a much more precise narrower range and closer to 14,600. But clearly there was melting going on throughout that entire. So again, it's like probably just some of the discrepancies in defining the terms.
And so that's because I was surprised by that too when I looked that up, because I thought it was a lot more defined.
Yeah, a lot more precise.
And it is in a lot of the studies. It is a lot more defined. I believe there was a Heinrich event right there at that episode, at that date. But that was the whole thing about the Bolling and the Alarod, was that you had this with some interruptions there in between. You had basically a phase of warming that lasted about at least 2,000, maybe closer to 3,000 years. And it was that warming that I think was probably consistent with the Milankovitch changes in solar radiation, which would be a slower, prolonged warming of the Earth, right? Because of the changing orbital geometries, right? So then it was that warming that was interrupted by the Younger Dryas at 12,860 or whatever the most refined date presently is. I still use 12,900 because it's a nice round number, easy to remember, and it is within the margin of error. So, but yeah, so then that is the lower Younger Dryas boundary, let's say at 12.9, interrupted that Bolling-Alarod warming. Now, my impression from the work that I read, and I'm going to have to review some of it, and maybe we can talk about it in the next episode, was that initial warming, that there was a very substantial spike of warming that that kicked off the whole Bolling-Alarod. And it was this spike of warming that fell right at about 14,600 years. And in fact, it shows up in the tree ring graphs that we've looked at 100 times, that there is that huge spike right there at 14.6. The dates have ranged most of the dates I've seen have ranged from 14.5 to 14.7, right in there. So you take the mean of that, it's going to be about 14.6. And that was that first spike of warming that you can see so clearly in the Greenland ice core record.
And what is the name of that period? Is that the beginning of the Bolling-Alarod? Is that Is that what it is? Okay, yeah. And then apparently there's a very short period in there that they are associating with a Maunder minimum where it gets cooler again for a little bit. Is that right?
Yeah, but now the Maunder minimum, that is in the Holocene.
They call it a Maunder type minimum.
Oh, well, a Maunder type minimum.
Yeah.
Okay, yeah. So right.
Yeah.
But the Maunder minimum itself is Holocene.
Okay. So from the paper, they say after the late glacial maximum, dated in the area at 21,000 BP, rapid warming accompanied by increased precipitation led to an intense erosion of slopes, generating colluvial to alluvial sedimentation and the formation of wide and deep alluvial fans characteristic of the subalpine landscapes. This created the so-called main post-glacial infilling, or MPI, which took place between 14.5 and 7,000 BP. Throughout the MPI, with its high sedimentation rate, many trees were buried, and these trees stayed well preserved and buried until their recent exposure following the vertical incision by the rivers. Erosion of riverbanks during the winter season reveals new subfossil trees almost every year.
Mm-hmm.
So in total, 172 subfossil trees were discovered in a 500-meter long and 30-meter wide stretch of the Druzé River. The trees are buried in France, in the Southern Alps. The trees are buried in loamy deposits of the MPI, forming a 2-meter thick alluvial terrace. This terrace contains 3 rooting levels, that are very difficult to differentiate because the loamy alluvial deposits are lenticular and discontinuous and only partially preserved.
Yeah, but in that photograph we were looking at, typically, if the gray area that Brad was referring to, that's probably the loamy deposit.
Yeah, yes.
And then that grade looked like it graded into sand, but there was no real clear, distinct bedding plane between
That's
them.
right. They're lenticular. They're big lenses of deposits.
Yes.
And then the lenses themselves aren't well preserved, they're saying. So it's muddy.
Yeah.
So anyway, the 140 of those trees were sampled. 140 out of the 170 were sampled. Discs were air dried, and then they go through the whole process of all this, the analysis they did dendrochronologically, finding that there were 3 basic eras of trees, building a map of the years, and then determining where the spike was at 14.3. And
so
it's 1 year. This is like the key thing, is that they were saying that the difference in what they've been doing because of the Miyake test and what the normal dendrochronological work has been, where they sample 10 years at a time.
Mm-hmm.
These guys are sampling 1 ring at a time. In other words, annual samples.
Yeah.
And they're finding these enormous spikes in one tree ring
that you would miss it
Yes.
without that degree of resolution.
That's right. You miss it because it
a
gets
very
spread out.
important point.
That's right.
And yeah, again, your sampling range can bias if you have very significant spikes that might leave an imprint, like
Yeah.
the radiogenic. Yeah, if you don't sample every year, you
The
could
spike
miss
just
it.
sort of disappears into a little bump, right? It's just a
Yeah.
tiny little, exactly, because it gets spread out among 9 other years with no spike.
With no spike. Exactly.
Yeah, exactly right. So it gets averaged in, and then it's almost gone. So so the graphs that they've built in the paper, and maybe Brad can put the links to the paper in the show notes, because there's a lot of graphs, good pictures. But the graphs they've built, they show that the spike is, it's not there, and then it just appears exactly at 14.3 to 14.299, and then it's gone. Completely gone in the next year, in the next ring. So there's a bunch
and then they went and backed it up by looking at the ice cores.
That's right. Then they looked at the ice cores and found a corresponding spike of beryllium-10.
So that would suggest to me that typically, if you've got, when you mentioned the Maunder minimum, if you've got a period of solar activity, typically you have less bombardment of galactic rays. So the galactic rays, which can produce radiogenic compounds like beryllium-10 and carbon-14, but the sun can also. But under normal circumstances, the solar wind acts as the buffer.
That's right.
That mitigates that bombardment of the upper atmosphere by galactic rays. Okay.
Right.
But in the case of like a coronal mass ejection,
a very powerful one, like one that's
a very powerful
enormously
one.
strong, where it generates the same kind of fast, heavy particles that a supernova makes. Yeah.
And that would be, now see, if you have a solar minimum, typically a solar minimum is spread over decades. So the fact that you have a spike that's focused into a single ring suggests that it was a very quick event.
Yeah.
Which would be more consistent with Earth encountering a coronal mass ejection, which is going to be a very short-lived event as contrasted with a longer spread out event, which is increased galactic ray bombardment because the sun has gone into a state of reduced activity.
Right.
Like the Maunder minimum. How long did the Maunder minimum last? I mean, it was decades.
Yeah, that's right. So the solar minimums in general generate more cosmogenic particles because of galactic cosmic rays.
Right.
Yeah, that's right.
Important difference there.
But other things that can do it, like cause a pulse, is like a nearby nova.
Yeah.
Or supernova. The thing is that people would expect, we would see evidence that if there was a supernova that happened close by enough to cause this spike, we should still see evidence of it out there if it's only 14,000 years old. But I just do think it's interesting. Like, there are other possible causes, but the most likely one seems to be a massive solar outburst. And the fact that this guy Miyake has found so many of them, they're not uncommon. That's the thing, is when in some of the articles they're listing them off. It's like 900, 700 AD, going back all the way to 7,000 BC. They're finding these spikes.
And I know that 700.
Each one of these spikes that he's finding is around like an order of magnitude higher than
the Carrington
more
event.
Powerful than the Carrington event.
Right.
Yeah.
The one that we have historically is the Carrington event, and the Carrington event was not strong enough to leave a record like this in the tree rings.
Right.
It didn't cause a spike in C14 that is visible to modern instruments.
But it was strong enough to induce enough current into telegraph wires to burn up the telegraph stations. They turned into conductors for heat and just
burst into flames.
Into flames. So it's like you have an order of magnitude higher than that. What would it do?
Or possible 2 orders of magnitude for this 14.3 one. And what it would do to modern civilization.
Yeah. This spike is even greater than
I would think it's a safe assumption that it would be a major disaster.
Absolutely.
Yeah.
Yeah.
Well, we were talking about this, like transformers, even your stockpile of transformers, if you get, it doesn't have to be connected to anything.
They just become an
this
inductor.
huge coil of wire, and the event can induce a current in that wire and heat it up. They can burn up just sitting in a warehouse.
Yeah. Not plugged into anything.
So we would lose all the transformers and have no stockpile.
And then how do you rebuild the electrical grid when there's no electricity to build more transformers?
We would be right back into the early 19th century.
Yeah.
Lifestyle.
Then the food supply collapses.
Yeah.
And the global transportation collapses. And you basically, it's the end. It's not an extinction event, but it's the end of civilization. Yeah.
As we know it.
Right.
Yeah.
And that was 1859, so 160 couple years ago.
Yeah, the Carrington event.
Yeah, which was not enough to put a marker in a tree ring.
It was a small event compared to what we're talking about, what you're introducing here, and these Miyake events that could be cyclic, don't know, but you're saying 700 BC, 900 BC, so a couple hundred years they happen.
Yeah, there's a whole list of them, and these are just ones that they found that Miyake was finding evidence of in specific trees that were from Japan, right? So like the work needs to spread and go worldwide and see if they can find more, and that's kind of what these guys were doing here.
And
with these trees
it's the single year spike,
right?
For all those Miyake events, it's just
1 year,
more or less instantaneous. Yeah. Not the decadal. Yeah,
that's right.
And so that just doesn't seem consistent with like a supernova type event.
Yeah, a supernova in the sky can last a year or two, right? So I was thinking like, or at least the visible part of it.
Yeah, and so, but this is now showing that there were events separated by intervals, so there was multiple events.
That's right.
Now, am I getting this picture right? There was a cluster of events around that 14,300 year ago.
What they said they found was an overall uptick in C14 and beryllium-10 that's they associated with a Maunder type minimum. That would lasted 100 years.
100 years, okay, yeah.
But in the middle of that, there's this massive spike.
Yeah.
Of C14 that was 1 year long right at 14.299 that they say must be a massive solar outburst in the middle of a minimum, which is really interesting, right?
Mm-hmm.
If you have a sun with no activity, you associate that with no sunspots, no activity. It doesn't have any flares, but then there's this enormous outburst, which is possible, right?
Mm-hmm.
A minimum sun does not have no sunspots. It just has very few.
So this is where we were talking about the possibility of like a comet impact into the sun.
Yeah.
During a minimum, causing a major storm. Like, is that, if the nucleus impacts in the sun, could that be the cause of like a huge solar storm, like something hitting the sun or whatever? So that would be, I don't know.
Yeah.
It's just spitballing, but.
Yeah, that's us speculating. Right?
Yeah. Well, let's go into that a little bit more. I've got some stuff here from, actually 2 decades ago, but it's relevant. Now, this was work that was being done, because by early 2000s, we'd had a decade of solar observations, satellite-based solar observations. So this is when some of the data started coming in. And then we also had, paleoclimate studies and things like what this paper is talking about. And this was from an article in the journal Science in 2001 talking about the work of Gerard Bond. You might look him up, Kyle, while we're doing this. That would be Gerard Bond, B-O-N-D, Bond. So this is what the discussion of his work says here in an editorial in the journal Science. Most scientists have long assumed that the sun shone steadily. Its unvarying brightness, the one constant in a climate system that seemed to lurch willy-nilly from one extreme to another over the millennia. Okay? From time to time, a few brave souls would suggest that the sun actually waxes and wanes with a steady beat, driving earthly weather or climate in predictable cycles. In a paper published online this week by Science, paleoceanographer Gerard Bond of the Lamont Doherty Earth Observatory in Palisades, New York, and his colleagues report that the climate of the North Atlantic has warmed and cooled 9 times in the past 12,000 years, in step with the waxing and waning of the sun. Quoting glaciologist Richard Alley, it really looks like the sun has mattered to climate. Then it goes on, the test for a sun-climate connection comes when the two types of records are put together for comparison. The more in sync the sun and climate are, the more it looks like the sun is driving climate change. Quoting Bond, it's a strong result. You can do statistics on it. But what really persuades him is what you see in a plot of the two records, the close match between the peaks and troughs of the climate record and those of the solar record. So I think one important point here is that even more than 2 decades ago, the climate-sun connection was already very robustly demonstrated. And here we are over 2 decades later, and the role of the sun is still pretty much totally ignored. But the evidence that we have collected and that has accrued in the time since this work was done has just gone even further to support the idea that the primary driver of climate on the earth is the sun, and changes in the sun are what causes the primary driver of the warmings and coolings on the earth.
Shouldn't that be obvious?
Well, one would think.
It seems like it should be obvious.
It should be obvious. Damn.
Yeah, I can actually.
So, did you say this? I mean, I'm looking at the Wikipedia of this guy, and now it's saying that Bond events were previously believed to exhibit a roughly 1,500-year cycle, but the primary period of variability is now put at 1,000 years. Did you already say that?
No, I didn't.
Okay, because I was reading while you were talking. It's hard for me to listen and read at the same time. This is fascinating. How come I've never heard of this guy?
Well, I knew the time was now that Kyle needed to know about this guy.
I knew you were holding back facts.
I have been holding back for a couple of years now, Kyle, until I felt that you were ready.
So he was awarded the Maurice Ewing Medal, which I've never heard of also, but it's
yes, you have.
I
Yes, you have. Maurice Ewing was essentially the founder of oceanography and marine geology. And back in the 40s, he was the one that went and did that, traverse over the sunken Azores and took samples. And the ship that he was aboard was called the Atlantis. And in those first 2 articles that I referred to from National Geographic in the Atlantis recordings that I did is based on the work of Maurice Ewing.
Okay, so this medal, this award is the Maurice Ewing Medal. It's 2 international geophysical societies offer awards each year, which are named in honor of Maurice Ewing.
Mm-hmm.
The Great American Geophysical Union and the Society of Exploration Geophysicists. They awarded this guy Bond the medal fall meeting honors ceremony December 2003. So I find this interesting that a guy that's saying the sun causes these giant cycles of amplified variability in the northern hemisphere climate got this award. Why isn't this?
Well, because you've got to understand that there's the science of climate change and the politics of science change, and the politics of climate change is very selective as to what research and what data they're going to reference, and then whatever they do not cherry pick to support the climate crisis narrative is completely ignored. So this is just more evidence of how, the data out there and research that's out there, work that's out there, is being ignored in the contrivance of this politically based agenda of anthropogenic driven climate crisis narrative.
Well, to me, it just shows that there are.
And you said
there are real scientists out there.
You said the cycles are
absolutely.
About 1,000 years.
Yeah, they've now changed it to about 1,000 years. But I mean, the fact that two societies would come together and award this guy is kind of like an affirmation, like a little private affirmation that they're like, yeah, we know what's going on.
So this is interesting then. A Miyake event is an observed sharp enhancement of the production of cosmogenic isotopes by cosmic rays. It can be marked by a spike in the concentration of radioactive carbon isotope 14 in tree rings, also beryllium-10 and chlorine-36 in ice cores, which are all independently dated. At present, there are 5 events that are known: 7176 BCE, 5259 BCE, 660 BCE, 774 CE, and 993 CE.
The one at 774, that was a really powerful one.
Yeah, so that's 774 AD, right? And 993 AD. Yeah. And then there are 12,350 BCE, 5,410 BCE, 1,052 CE, and 1279 CE that need independent confirmation, according to this Wikipedia editor. This data yields the average occurrence rate of roughly 1 event per 1 to 2 millennia. The strong evidence that Miyake events are caused by extreme solar particle events. They are likely related to super flares that have been discovered on solar-like stars. Although some events might have taken seemingly longer than 1 year, they are still consistent with the solar scenario. The biggest Miyake event so far discovered occurred in 12,350, which I think this hasn't been updated yet to this new paper.
Now, is that if it's before Common Era, BCE?
That's right.
So that would be the 14,000.
Oh, yeah, you're right. 14.3. Yeah, that's right. Yeah. Okay, so this newly identified 14,300-year-old storm is roughly twice the size of the most recent events, 774 and 993 CE events.
So so that puts it probably several orders of magnitude more powerful than the Carrington event.
Yeah. So a Miyake event occurring in modern conditions might have significant impacts on global technological infrastructure, they say.
So if the Carrington event, which is 1859, was one of these events, just a very mild ridiculously mild one, then, and they're 1 to 200 years, 1959 and then 2059.
Yeah.
So we would be in the window of another one.
Yeah. I'm going to share a screen here. Are we seeing the graph of the?
Yes.
Yeah, great. So if you look here, iceborne debris is shown by black curve. Fluctuations of carbon-14, a proxy for solar change, are shown in blue. The correlation between the two is strikingly obvious. So what's happening here is, iceborne debris. So what that is you've got these events, these Heinrich events that are dumping huge amounts of gravelly coarse material into the North Atlantic on pulsed episodes, right? So you've got the normal accumulation of sediment, fine-grained sediment, interspersed with these much more coarse gravelly layers. And those are because you've got these giant armadas of icebergs being disgorged from the Laurentide ice sheet. I don't know about the Fennoscandian, but certainly the Laurentide ice sheet, these vast armadas of icebergs are being disgorged into the North Atlantic. And as they drift south, they begin to melt. And of course, those icebergs have a massive accumulation of debris and material that they've scooped up from the surface of Canada. That stuff then, when the icebergs melt, that stuff dumps into the ocean, falls to the bottom, and forms a very distinct layer. Well, and what we see in this graph here is this really strong correlation between those kinds of events and the sun.
And there's like a pretty regular frequency there too, but it as you go back, the big peaks and troughs get closer together.
Mm-hmm.
They're like 2,000 years apart all the way back, and then up near the modern times, they're like 3,000. Closer to 3,000.
This is showing a very large spike right there. It looks like 11. It would be probably around 11.6. This is probably now the marker of the transition from Pleistocene to Holocene right here. It looks to me, if you project this down, it looks to me like it's going to be very close to 11.6. And then you've also got this huge spike of debris dumped into the North Atlantic, which means there was a massive disgorging of icebergs correlated with that. So the point is here, the sun has no effect on climate. Let's just ignore it.
Yeah, it looks like a flat line to me.
Yeah.
No effect.
No effect.
That's just a trick. It's just you just
average it out. Yeah.
Yes, people, this is sarcasm.
Yeah. So just real quick, this is interesting to me, but I do want to say this: these events, the Miyake things, are named after physicist Fusa Miyake, whose team was the first one to identify these annual radiocarbon spikes, and they published the results in 2012 in the journal Nature. They found at the time a strong C14 increase in the annual rings of Japanese cedars for the years 774 and 775. This event was independently discovered, and in 2013, the same team published the discovery of another similar spike in the years 993 and 994. So that's why they're named after this guy, a physicist.
Mm-hmm. So this is the work of Louise K. Harrah, Harri, published in the Philosophical Transactions of the Royal Society of London, also way back in 2002. And the title of the article is Explosive Events on the Sun. And here's what she says. I describe two of the most dynamic and highly energetic phenomena in the solar system. The explosive flares that can occur when plasma is confined by magnetic fields, and the large-scale ejections of material known as coronal mass ejections. Now, this is very interesting because this takes us bumps up right against the whole phenomena at work in the plasmoid technology, which is the containment of plasmas, the confinement of plasmas by magnetic fields. However, there's a difference, and the difference is the origin of the plasmas. Is the plasma coming from air/fire or from water? Okay, now here obviously we're talking about fire. We're talking about the sun. So the explosive flares can occur when plasma is confined by magnetic fields and the large-scale ejections of material known as coronal mass ejections. These explosive events are poorly understood and yet occur in a variety of contexts in the universe, ranging from planetary magnetospheres to active galactic nuclei. Understanding why flares and coronal mass ejections occur is a major goal across a wide range of space physics and astrophysics. Although explosive events from the sun have dramatic effects on Earth, flares in other stars, for example, can be vastly more energetic and have an even more profound effect on their environment. So one of the questions that has been raised now when we're looking at other solar type stars and seeing these vastly more energetic and much larger events is, well, are such events potentially occurring with respect to our sun? That's one of the major questions that's raised as we're looking at other solar type stars and seeing these massive events occurring, much more energetic than anything we've, monitored or measured recently on our sun. It raises the question. And it certainly does point to the fact that a lot of these solar type stars are seen to have these enormous energetic outbursts, which suggests that our sun is an anomaly if it's not doing that.
You'd have to argue that our sun was special somehow.
Yes.
And that to say that it doesn't do that. Yes, that's right.
To say that it doesn't do that.
Exceptionally stable.
Yeah.
And now remember, this is going back to 2002. Now we have over 20 years of data on top of what this is right here, right? But she goes on in her report saying, we are now in the unprecedented position of having access to a number of space observatories dedicated to the sun. The Yoko spacecraft, the Solar and Heliospheric Observatory, the Transition Region and Coronal Explorer, and the Ramati High Energy Solar Spectroscopic Imager. These cover a wide wavelength range from white light to gamma rays with both spectroscopy and imaging, and allow huge progress to be made in understanding the processes involved in such large explosions. The high-resolution data show dramatic and complex explosions of material on all spatial scales on the sun. They have revealed that the sun is constantly changing everywhere on its surface, something that was never imagined before. There are two main types of explosive events on the sun: solar flares and coronal mass ejections. Impulsive energy release in solar flares is one of the most dynamic and highly energetic phenomena in the solar system. The process is poorly understood and yet occurs in a variety of contexts in the universe: solar flares, planetary magnetospheres, active galactic nuclei, which I already read. Coronal mass ejections can pour 10 to the 13th kilograms of material into the solar system in one event. This is approximately the mass of Mount Everest released into the solar system once per day. Much has been learned over the past 10 years, and again 2002, about the working of explosive events and their origin. The ultimate goal now is to understand the actual trigger of these spectacular events. The combination of the missions described in the previous section will provide an entirely new view of the sun, from very close up to 3 dimensions to looking below the surface and linking the surface behavior to the corona. The next decade will unravel even more of the sun's mysteries.
So my question is, where are the balancing, according to Malcolm's physics, the implosive events? These are all explosive, right?
Mm-hmm.
Where and when and what capacity are those implosive events, and how do we experience those?
Well, see, that's what he was, I think that's kind of what his contention is that what we normally experience are the explosive events.
Yeah.
I wouldn't know the answer. I mean, couldn't come up with any,
Well, what's interesting though, just Brad bringing that up, is that even just standard model physics is telling us, if it's basically correct about stars, is that they are a long-term balance between an implosive event and an explosive event.
Yeah.
Right. The gravity is constantly trying to crush the material of that star down to a tiny sphere,
right,
or into a black hole or whatever. But the explosive event of the fusion is keeping it from happening, and then it just sits there for billions of years in this sort of strange equilibrium. And then you have these occasional flares where something is escaping this equilibrium that's been built between the implosive and explosive forces.
Quasi balance.
Yeah. But eventually it'll run out of fuel and it will implode. That's the idea.
Mm-hmm.
And that implosion causes another explosion. It's like, a never-ending cycle.
Yeah. It passes the point of equilibrium.
Yeah.
Right? It's like a pendulum.
Yeah.
It implodes too far.
Right.
Which causes it to explode too far. Does this for a while.
Well, it's break time. Hey. You want to take a quick break, Randall?
Sure, let's take a quick break.
All right. We'll be right back.
Do it.
All right, folks, we're back. We are back. Second half of show. We just probably recorded a Patreon segment in the break there, and there was a lot of interesting talk before the show as well that might also go on the Patreon eventually. Don't quote me on that. Brad's got a lot of work to do, and he's also traveling a lot.
Help out Randall, help out the group, the podcast, get better, and more often patreon.com/Randall Carlson.
Yeah. So are you're trying to put more content on the Patreon, Brad, or what's the?
Yeah, definitely. We've got bonus content, and it's just having the help to do it all. And Laura, our art director, that does the website now and does the graphics, and she's also taken on some editing duties. Has learned
wearing
to edit
many hats.
Yeah, she is. Social director for the tour events. She's learned to use an editing program on her phone. So she puts together some short videos and some longer videos. But yeah, she's been grabbing some of the stuff that's behind the scenes, the non published parts of the podcast beforehand, during the break, post podcast, and making that available. So yeah, we're getting better about giving some regular content to the Patreon supporters, because we really appreciate them, and we need more. There's so much content, and it takes time and effort to get it out there.
Well, just give it to them raw, Brad. Give the Patreons just the raw stuff.
Well, that's
make it easy on yourself.
I made it available into a folder, and Laura took it and then made it available, and I didn't even know about it. I got the announcement because I am also myself a contributor, so I get the announcements, and I also support $50 Dynasty and Brothers of Serpent, and you all should do that also.
We also have Patreons,
coming out by those guys, music and info. But she posted something. I was like, well, hey, let me know what you're doing. I want to see it. It's like, so yeah, she's grabbing it and going. So there's a lot more than there used to be, and we're gonna keep that coming.
Cool. So thanks to everybody who donates to podcasts. We all appreciate it. It is a lot of work for people other than me
and Mike.
I just get to sit here and hit record, throw a file up on the server.
This is Kyle.
That's his job. Job done.
Job done.
Good grief. Randall's making me look things up. Anyways, what else are we going to look at, Randall?
Yeah, where are we going?
Come on.
Yeah, good.
Give us show content.
Hey, this is here. Okay, we got to get serious. This is serious stuff, you guys. We can't be laughing, making light of this serious stuff.
We're talking about the dog star? Oh, sorry.
Yeah, be clear.
Terrible.
Yeah, we still need to have that conversation about the dog star. There's a few things
that I serious conversation.
It is a serious conversation, man.
It's a serious conversation. About,
all right, I'm sorry. I'll stop. Go.
Here I was ready to go. Now you've got me all distracted.
Doggone it.
Let's continue on talking about the sun a little bit. I have some actually pretty interesting things here. Jumping this is 1999, but nonetheless, and actually, I've got some new studies that were done by Judith Curry, the former
Georgia Tech
climatologist at Georgia Tech, who basically had to leave because she went with scientific truth rather than the propaganda, and she definitely deserves recognition for that. That her scientific integrity compelled her to leave Georgia Tech rather than get on board the narrative.
Yeah, definitely look her up, Judith Curry.
Yeah,
with a C.
Yeah, she's one of my new heroes. Anyways, she's okay. We're going to go back to 1999 now. This is in Nature, a doubling of the sun's coronal magnetic field during the past 100 years. The solar wind is an extended ionized gas of very high electrical conductivity, which is one of the things we know now about plasmas, is that they're electrically conductive. And therefore drags some magnetic flux out of the sun to fill the heliosphere with a weak interplanetary magnetic field. Magnetic reconnection, the merging of oppositely directed magnetic fields between the interplanetary field and the Earth's magnetic field, allows energy from the solar wind to enter the near-Earth environment. The sun's properties, such as its luminosity, are related to its magnetic field, although the connections are still not well understood. Moreover, changes in the heliospheric magnetic field have been linked with changes in total cloud cover over the Earth, which may influence global climate. Here, we show that measurements of the near-Earth interplanetary magnetic field reveal that the total magnetic flux leaving the sun has risen by a factor of 1.4 since 1964. Surrogate measurements of the interplanetary magnetic field indicate that the increase since 1901 has been by a factor of 2.3. This increase may be related to chaotic changes in the dynamo that generates the solar magnetic field. We do not yet know quantitatively how such changes will influence the global environment. But what do you suppose the conclusion would be? That it does not or does influence the global climate?
It must.
It
must.
Of course. It, yeah. Yes.
Yeah.
Because it is all an integral machine, if you want to look at it that way.
Yeah, and it's also that I just always try to keep in mind, the sun's energy levels are so high that tiny changes represent an enormous amount of energy, plus or minus, right? So it's it definitely would have an effect.
I just saw a news story, surely from a paper, about how the solar activity affects the cloud cover on one of the distant planets. Let's just pull it up real quick. Well, I see one saying it has direct impact on Earth's cloud cover. But yeah.
I think that's, at this point, pretty well established. Remember, this is research going back to 1999.
Yeah.
And what about subsequent research? Well, the subsequent research supported this or refuted it? Well, I think clearly supported it. this idea of changes in the solar luminosity.
And did you say that they were pulling? They had information from back to 1901. They said what was that information? How are they getting that data?
Well, we can go back to the original paper, which I don't have in front of me.
Well, you had a quote there. What did they say about the data going back to 1901?
Oh, okay. Here we show that measurements of the near-Earth interplanetary magnetic field revealed that the total magnetic flux leaving the sun has risen by a factor of 1.4 since 1964.
Okay.
Surrogate measurements of the interplanetary magnetic field indicate that the increase since 1901 has been by a factor of 2.3.
Okay, so they have, like a proxies or surrogate measurements.
And the increase may be related to chaotic changes in the dynamo that generates the solar magnetic field.
Right.
Okay, translate this idea of solar flux into temperatures on Earth.
Well, cloud cover has a major effect on Earth climate.
Yeah, and surface temperature and everything.
Well, yeah, and actually,
but you were talking about solar flux, right?
Yeah.
Mm-hmm.
How does that translate directly into surface temperatures on Earth?
Well, I think we just have to look at empirical data. So if we jump ahead 1 year to the year 2000, in Quaternary Science Reviews, there was a paper published that was entitled "Past Global Changes and Their Significance for the Future." And it's by Raymond S. Bradley, Quaternary Science Reviews. So I'm quoting though. Although a few instrumental meteorological measurements extend back into the 17th century, no extensive network of data exists prior to the mid-19th century. Hence, although we may have a 300-year record of climate at a few specific locations, we have only approximately 150-year perspective on the spatio-temporal variability of the Earth's climate system as a whole. The paleotemperature reconstruction of Mann et al. Also shows that abrupt short-term changes in temperature have occurred over extensive regions. Of particular note is the sequence of years 1834 to 1838. The year 1834 was the warmest in Europe over this period, with overall temperatures approximately 0.7 degrees above the 1902 to 1980 mean temperature. However, in the next 4 years, temperatures systematically fell to the coldest year of the entire record, 1838. For marginal agricultural societies, this sequence of cold years was catastrophic. In the central mountains of Norway, for example, harvests were damaged by early frosts, leading to starvation. And in Japan, there was widespread famine in 1836. Similarly, dramatic cooling also affected North America, where 1837 was the coldest year of the last 250 years. This rapid change was due to radiation and circulation anomalies associated with the explosive eruption of Kosmographia in January 1835, which is I probably am mispronouncing it, but that was the name of a major volcanic eruption. Such unpredictable events clearly have a major impact on temperatures over extensive parts of the globe. Yet even the largest historical eruption was small compared to numerous late Holocene eruptions recorded in Greenland ice cores. If similar magnitude eruptions were to occur today, the rapidity of temperature change would likely have a devastating effect on society, even in a warmer greenhouse world.
So there But there is no like formula or any statistical evidence, no correlation between.
There is work being done like that.
But okay.
There is.
But I think if you're asking, like, is there a direct correlation?
There's no scale, but there are no comparative scales or anything like that.
Well, it depends. Yes and no. There are people, solar physicists, working on this as we speak. It's an ongoing area of research. They're still correlating through, 2+ decades of solar observations that have been made that weren't available a generation ago.
Well,
there's a lot of data there.
Which circles back to a point you made earlier, you were making earlier in the previous segment about sun activity, and it's always been thought, well, sun activity doesn't have much to do with the climate on Earth.
That's the assumption, yes.
But because we don't have the data, because has been no data, because we haven't had the ability to study the sun until the middle of the 20th century, how would they know? So they're just making this assumption that the sun's cycles have nothing to do with Earth's climate.
That's right. It's it's based the idea is,
and yet common sense would say yes.
Of course it would.
Yeah.
Well, let's go on with what this guy's report then goes on to say. The melt record from polar ice caps is a fairly simple and direct measure of local summer temperature. Melt layers occur when surface water percolates down and refreezes within the firn, which is the snow gets compacted into firn, which FIRN, which gets compacted into glacier ice. So firn is that intermediary transitional zone between snow and glacier ice. Okay. So you have surface water percolates down into the firn and refreezes. Then results from the Agassiz ice cap in the Canadian high Arctic show clear evidence of early Holocene warmth with extensive melting on this approximately 2-kilometer high polar ice cap, driven by increased summer solar radiation. These conclusions are supported by a similar melt layer study of the JISP-2 ice core summit Greenland. Melting was virtually zero just prior to the 20th century, representing a cold episode rarely surpassed in the entire late Holocene. But in the last 75 years, it has increased to levels only exceeded twice in the last 4,000 years. Conditions in the high Arctic in the 20th century were thus atypically warm compared to the rest of the late Holocene. But equally remarkable, and this is what needs to be kept in the front of your mind, is the fact that the preceding cold episode was one of the coldest in the entire Holocene. So all discussions of modern global warmth, the baseline is the coldest point of the last 11,000 years. Now, that needs to be factored into one's thinking if one's going to come to certain conclusions about the unprecedented nature of the current warmth that we're experiencing. Let's go on. Varved sediments from southern Baffin Island at about 65 degrees north latitude, and tree ring studies from across the North American tree line enable quantitative paleotemperature estimates to be made and confirm that summer temperatures were considerably lower in the 18th and 19th centuries compared to the warmest decades of the 20th century. On southeastern Baffin Island, for example, mean June temperatures were approximately 2 degrees centigrade lower from AD 1700 to 1900 than in the last 50 years, leading to less snow and ice melting, reduced runoff, and minimal sediment flux to rivers and lakes. During this period, upland plateaux were extensively and persistently snow-covered. Tundra vegetation on the hilltops was killed, and glaciers advanced to positions commonly more extensive than at any other time in the Holocene. So again, if we're going to talk about glacier recession, we have to keep the baseline in mind. The baseline in this case happens to be that we're looking at the recession of glaciers from the point at which they were the most expansive of the entire Holocene. So obviously, without having a longer-term perspective on the behavior of glaciers, we aren't going to be able to create realistic models. That should be pretty clear. So then we have macrofossils, basically trees and branches located above present tree line in the Skandies Mountains of Sweden provide another record, indicative of summer temperature throughout the Holocene. The upper limit of trees in this region is very sensitive to summer temperature. By mapping the uppermost occurrence of trees as recorded by remnant pieces of in situ subfossil wood, a record of summer paleotemperature is revealed. Because a very large number of samples has been collected and dated, a fairly complete record of Holocene tree line changes can be reconstructed. Like the Agassiz ice cap summer melt record, cooling throughout the Holocene is again clearly revealed, with the most recent cold episode also being one of the most severe in the entire record. So the epoch immediately subsequent to the deglaciation, the transition from Pleistocene to Holocene, say between 11,000 and 10,000 years ago, was warmer than now. And what has happened is this climatic optimum that it was originally called, now it's changed, the term has changed to the hypsothermal. The 3,000 to 4,000 years of the climatic optimum then gave way to a steady, gradual cooling with interruptions that culminated in the Little Ice Age. And in the mid-19th century, the planet began to come out of the grip of the Little Ice Age. All right? So now what they're doing is they're looking at tree lines fluctuating up and down, which is going to be a diagnostic of temperature. So further insight into the biological significance of this period is provided by studies at the tree line in the northern Ural Mountains of Russia. So they're looking at multiple places around the world, okay? There, in situ or situ subfossil trees were cross-dated to provide precise information on when each tree was established and when it died. This study shows that in the 12th and 13th centuries, trees were able to establish themselves and grow successfully at elevations up to 340 meters above sea level. But over the next 400 years, the upper limit for the tree establishment gradually declined. Many high elevation trees died, and from 1750 to 1950, no seedlings at all were able to survive above 280 meters. So right up until the middle of the mid-century, 280 meters is as high as the trees. They couldn't survive above that. Yet, between the 12th and 13th century, the trees were going up to 340 meters above. This situation has only changed in the last approximately 50 years. This was written in 2000. And trees are once again becoming established at elevations above 300 meters in this region. Can you say then that at least in terms of the climate's effect on tree lines, is there anything unprecedented? Well, clearly not. Simply saying it's just they're just once again becoming established at that level. And that piece of information completely confirms and supports all kinds of other evidence from other areas of research that the medieval warm period was warmer than now, or that really all we're doing is after the cold of the Little Ice Age, we're returning to the levels of previous warmth. I mean, that is the only thing that you can really claim with any kind of certitude. Now, the question then becomes, all right, given that it is not unprecedented, that the modern warmth is not unprecedented, then why can we immediately dismiss whatever forces or factors were driving climate 700-800 years ago, that they are completely non-operational now? And this replication of what has gone before is something completely new and different, that is humans burning fossil fuels? All right, can we make that leap with certainty and then proclaim that's the end of the discussion and it's settled? I don't think so. Okay, so now here's the question I think that we could even begin to talk about. I'm going to maybe do another graph here. Let's do this. So I will do
just real quick while you're doing that.
Yeah.
I did find the story. Smithsonian Magazine has it that they're finding a very strong correlation with cloud cover on Neptune and the solar cycle.
Mm-hmm. Sure.
So we get images of Neptune every time it comes closest to the Earth, where we can see the clouds from using the Hubble Space Telescope, and they're correlating it to. So after the highest point of activity of solar activity, like within a couple of years, Neptune has like its cloudiest period, and so then as it goes into the solar minimum, then all the clouds disappear.
So I think that could support the conclusion that we could have a high degree of confidence in the fact that if solar cycles are affecting cloud cover on Neptune, which is how many farther times away from the sun than the Earth, that the sun would be having a similar type of effect on the Earth.
Yes.
Oh, but no, it's the sun. No. Just to talk about sun. In fact, this latest paper by Willie Soon, he gets a lot of heat because he's been one of the preeminent scientists of the last decade or two, pointing out the correlation between climate change and solar change. And he has really, if you look up the things, the smear, the hit jobs, the attempts to discredit Soon, because his research goes so glaringly contrary to the narrative. Because his work, along with a whole bunch of others, shows that the sun is clearly the dominant factor in terrestrial climate change. And I'm going to do a share screen here. Another one, share screen. Let's go to screen 3. All righty, then. Are you seeing this graph, I think?
Yep. Yes.
All right. So the bottom, look at there. You got from the year 1600 up to the year 1740. And there's your Maunder minimum. And again, that is coinciding exactly with one of the really cold phases of the Little Ice Age. And it was the year, and then you had the Dalton minimum here. And that again coincides, 1816 was the year without a summer. And I think that, we've talked about that. And I think the argument could be made that what you've got there is it's the combined forces of volcanism and reduced solar activity that cause these. And there could be a correlation. That's the whole thing. We're again, I think the model we have to begin conceptualizing is that the whole solar system is functioning almost as an integrated machine, an integrated system. So would the changes in solar radiation, affecting the things that we were just talking about, it's clear that those changes in the heliosphere now impact and affect changes in the Earth's geomagnetic field. Could that in turn then be related to bouts or episodes of volcanism or seismic activity? I think the answer would be, yeah, that it seems very possible with what we know now. Anyways, you look, this graph is very interesting. You also notice 1960, you have a big peak. So this is a time series of sunspot numbers since 1610. And so that's the sunspots being a direct yardstick of how active the sun is.
So that's an answer to your question there, Mike. I mean, that's a pretty good correlation between solar wind, solar flux, and temperature on the Earth.
And I'm sure that there's still a lot of work yet to be done before that relationship could be quantified, if ever, really, because we're dealing with natural forces of tremendous variability. But what we might do, I think, is come up with approximations that will allow us to, understand the connection between solar changes and climate change better than we do now. And a lot of research still has to be done. That's the point I guess I keep coming back to.
There's also some pretty interesting work going on right now about the impact of cosmic rays on cloud generation, right? On cloud creation. So during a minimum, when there's way less protection from the solar flux from like galactic cosmic rays coming in, there's a lot more of them hitting the atmosphere, and that may generate far more clouds. So not only do you have reduced luminosity from the sun cooling things off, but you have increased cloud cover from cosmic rays.
Well, one of the things that puzzles me, that I'm not puzzled, but curious about is, I used to run a photo lab. I've done some photography. We discuss photographic light in terms of Kelvin degrees, right? Like light of a certain temperature is a certain color. How do we measure? Are there measurements for the sun hitting the Earth? Do we measure that?
Yes, we do. Absolutely. Okay. I mean, that's a big part of what the solar observing satellites do.
And what kind of unit? How is it measured? Is it measured in Kelvin? Is it measured in
it's measured generally in like energy, so more like joules or something like that than a temperature.
Okay.
Like how much, like what is the amount of energy that the sun is putting into the Earth system,
right?
In a 24-hour period.
Okay. And what do those studies show? Is that what's represented on those charts that you were showing me?
I think the up and down on those charts was sunspot numbers.
Okay.
Those are sunspot numbers, which are directly related to. And so what this is showing is that during times so sunspots seem to correlate with periods of solar activity.
Solar maximums,
Solar maximums, right? Yeah. So when you have no sunspots, it means that the sun is in a more or less quiet phase.
Yeah, the sun has an 11-year
solar
cycle.
Right.
Yeah. So now we're coming out of a minimum and going back into a maximum slowly.
In the paper that graph appeared in, this is what they're talking about. Beyond the past 4 centuries of telescopic observations of the sun, the main tool for evaluating solar activity is provided by cosmogenic nuclides, which is what we were talking about earlier. The production of these isotopes is modulated by the magnetic properties of the solar wind, which can be ultimately linked to solar activity. After their formation, cosmogenic isotopes are transported in the atmosphere and the ocean before being buried in various archives. These processes make the interpretation more complicated. Nevertheless, studies of cosmogenic isotopes generally agree in indicating numerous solar activity minima in the past, with the sun passing a large part of its history in calm phases, conceivably with an irradiance several percent weaker than the present-day value. And I think one of the things we could then also say with a high degree of confidence is that just as we're looking at a mean value and we're talking about periods of calm phases with irradiance several percent less than the mean, we're probably also looking at periods with several percent greater than the mean, obviously, right? If we assume that the present is, in fact, a mean rather than a maximum. And I think it's almost certainly going to be a mean. So now the question is, do those periods of solar activity and solar calm correlate with climate changes? And I think the data that is now in robustly supports a correlation. Now, to what extent do we have formulas to quantify that? I don't know. I would imagine
there's probably not a direct formula for temperature, right, based on solar activity, but you can see a general trend.
Yeah. Well, so then we come forward to 2007. This was a paper that appeared in the Journal of Geophysical Research. The sunspot, auroral, and geomagnetic records all exhibit substantial long-term variations. All three, sunspot, auroral, and geomagnetic records, okay? All three exhibit active periods similar to that observed during the period 1950 to 2000 AD. Now, what's interesting, if we look at the climate graphs, you probably heard about the pause, that there was warming between 1950 and 2000, but essentially no warming overall since the year 2000. We can actually, we can cite the work in another Cosmographia episode. But anyways, all three periods exhibit activity similar to that observed during the period 1950 to 2000 AD, and quiet periods such as the three grand minima. The Spore, I think it's pronounced, from 1420 to 1540. Very cold period, right? The Maunder, which was from 1645 to 1750. I back up, 1715. 1645 to 1715. And the Dalton minima, which was from 1800 to 1830. Unlike the sunspot and geophysical data, there is no continuous cosmic ray record from the past centuries to the present. In this paper, 4 separate cosmic ray records are intercalibrated to allow us to study the long-term changes in the cosmic ray intensity between 1428 and 2005. In particular, this allows us to study the long-term cosmic ray changes since 1900 and to compare the intensities observed in the space age, 1965 to 2005, with those observed over the past 500 years. Okay, so now this paper, Mike, was published in 2007. So right there, you can see that these studies looking for these patterns and these correlations are undergoing. Nobody, I don't think it's going to stand and proclaim that, oh, we've got it all figured out, so we can move on now. This correlation has been quantified. Here's the formula. Just learn the formula. You don't need to know anything else. Let's move on.
Especially since those guys were probably working on the data of like the decade chunks, right? Where you're measuring C14 in 10 tree rings instead of 1. So now if we can get the higher resolution like these guys are doing for the Miyake events, you might see even more interesting stuff.
So it says that the neutron monitor record started in 1951. So I'm the same age as the neutron monitor record. I wonder what
who else you're the same age as? I just heard this the other day. I was surprised. Sting turned 72.
Oh, we did.
Yeah.
Hey, not to segue off, but how about the Mick Jagger, man?
Mick Jagger's going to be 80 in December.
He is 80. Yeah. I just saw a video of him doing his preparation for their next tour. And I mean, he's like, it's insane. Okay. So I've got a new model I'm going to emulate, Mick Jagger.
All right.
So when I get to be 80, I'm in the same shape that he's in now. My God, that guy, I got a hand. And
he got that way with clean living and constant prayer, right? Isn't that what he says?
I mean,
I'm pretty sure that's what it was.
Yeah.
Maybe it was sex, drugs, and rock and roll, but it could have been clean living and constant prayer.
Well, even Keith Richards has cleaned up his act.
Yeah.
So that the world has shifted some way. If Keith Richards cleans up his act,
yeah.
Clearly there's been a shift. So it's the most commonly used measure of the cosmic ray intensity at Earth. Since 1951, the neutron counting rates have returned to within approximately 2% of the same value in each of the sunspot minima in 1954, 65, 76, 87, and 97. And there is little indication of change in the residual modulation observed at sunspot minimum over these 4 solar cycles. So that's would be expected. I mean, because we have been in a period of relatively minimal amplitude climatic change compared to what we've seen in the past. Okay. But then we get to the part that I really find interesting here. Let's see, is this it? Okay, yeah, okay. So 2007, this is Advances in Space Research from a paper entitled Space Climate, and the Solar Stellar Connection. What can we learn from the stars about long-term solar variability? And that's what I was referring to earlier. This study of, with the advanced telescopic technology we now have, we're able to study these other sun-like stars. What it just says here, the sun's variable magnetic activity influences the heliospheric space environment within which sits the solar system with all its planets, including the Earth. So again, getting to this coherent, comprehensive, integrated model of the interactions among all the components of the solar system. I don't think we can take any single thing out of it. I mean, just looking at the size and spacing, the masses of the outer planets, the role they play in marshaling comets into the inner solar system, for example. Without that particular arrangement, the flux of comets to the inner solar system would be drastically different.
Yeah.
So, I mean, we could begin going down this list of the things that we're seeing, which, again, we have to think of the solar system as essentially as one world system, that it all is working together. The sun, the Earth, all of the planets, the comets, the space dust, the radiation from this, all of it. So we're looking for some kind of a comprehensive model, which I think we're approaching at some point. But it goes on to say, while flares and coronal mass ejections originating on the sun pose a serious hazard to astronauts, satellites, polar air traffic, electric power grid, and telecommunications facilities on short time scales on the order of days, the solar radiative output affects planetary and global climate on much longer time scales, from decennia to stellar evolutionary time scales. The sun radiates
billions of years.
Yeah, the sun radiates at different wavelengths. The total magnitude of this energy flux, its individual components, for example, invisible, ultraviolet, extreme ultraviolet, and X-rays, and the changes in them have important consequences for the evolution of planetary atmospheres, such as that of the Earth, including the synthesis of organic molecules and early life forms. Well, we had an interesting quote about space climate and the solar stellar connection, which is certainly something that'd be very interesting and worthwhile looking deeper into. And I'm sure we're going to have, especially now with the new telescope, hopefully we'll be getting more information and data on that. because I think ultimately we've got to look at our solar system within the context of the galaxy.
The James Webb or a different one?
James Webb, that's what I was looking for. Thank you, Brad. Okay, so 2009, this was from a presentation at the Preceding Union, Symposium number 257 in 2009. The conference was Universal Heliophysical Processes. This was the symposium. Okay. And this was from a paper, a presentation at this symposium entitled Explosion of Sun-Grazing Comets in the Solar Atmosphere and Solar Flares. Here's from the abstract. Explosive evolution of nuclei of sun-grazing comets near the solar surface, which occurs at conditions of intense interaction between the solar atmosphere and falling high-velocity comet nuclei, as well as the relation of the phenomena to the character of solar activity, are analytically considered. It is found that due to aerodynamic fragmentation of the falling body in the solar chromosphere and transversal expansion of the fragmented mass under the action of the pressure gradient on the frontal surface, thermalization of the kinetic energy of the body occurs by a sharp stopping of the disk-like hypervelocity fragmented mass near the solar surface within a relatively very thin subphotospheric layer, and has therefore an essentially impulsive and strongly explosive character. The specific energy release in the explosion region, in terms of ergs per gram, considerably exceeds the evaporation sublimation heat of the body, so that the process is accompanied by production of a high temperature plasma. The energetics of such an explosive process corresponds to that of very large solar flares for falling bodies having masses equal to the mass of the nucleus of Comet Halley.
Well, all right.
So this leads us in a very interesting direction, I think.
Comet Halley's like 10 miles across?
Yeah, and Comet Halley is not a particularly big comet. I mean, when you start looking at the giant comet hypothesis, from which the Taurid meteor stream is but a fragmented remnant, we're talking about a comet nucleus that could be 50, 60, 100 miles in diameter. Now, whether that mass makes its way into the sun as a single component, or it's fragmented and dumps into the sun over a period of a few thousand years, maybe in clusters of solar bombardment, could there be some type of a synergistic accumulation, a feedback loop of some kind that could be triggered within the solar chromosphere, and this in turn leads to a hyperactive sun? Well, from what this just said, it sounds to me like that's a potential plausible idea.
For the entire Holocene, perhaps.
Okay,
well,
so
that may
just
also
for
be
scale.
That may also be how you get a 2 order of magnitude larger than the Carrington event solar flare during a Maunder minimum like period.
Yeah.
In that paper we were reading at the beginning of the show.
Yeah.
If something really large, some large comet nucleus hits it, causes a massive flare.
So it goes on to say,
just let me throw that factoid in there for people that may be somewhat new to this for ratio and scaling. The sun is estimated at 864,000 miles diameter.
Mm-hmm.
So we're talking about a 10-mile plus or minus object. So yeah, really small in comparison.
Right. But interestingly, you see, as it approaches the sun, the super strong gravity is accelerating that object to just hypervelocity speeds,
sucking it
probably
in.
hundreds of thousands of miles per hour. So, and then, like it said, it basically pancakes out. Wow.
Yeah, being flattened out by the tidal forces.
It does a belly flop into the.
It does a belly flop. It does a belly flop. Mm-hmm. That's it.
Comet belly flops.
Comet belly flops.
Pancake.
Yeah.
I like it.
Frozen
so it goes
pancakes.
on to say, coronographic observations by Solwind, SOLWIND, which short for solar wind. The SMM, which is the solar maximum mission, and SOHO, which is the Solar and Heliospheric Observatory, 3 missions, satellite missions, indicate the presence. And see, we didn't know this before we started looking at the sun with satellites, right? Those missions indicate the presence of a continuous comet flow passing close to the solar surface or colliding with the sun. Passages of comet-like bodies, extrasolar comets near young stars may be responsible for observed changes in stellar spectra. For the origin of the Beta Pictoris-like phenomena due to evaporation of these bodies. We are developing an analytical approach to investigate the evolution of comet nuclei under the conditions of intense interaction between the solar atmosphere and falling nuclei, resulting in their aerodynamic fragmentation, as well as the relation of the phenomena to the character of solar activity.
Ooh.
Yeah, so interesting stuff.
That's very interesting. I need this paper.
Yeah, that interesting stuff is, in the words of Kyle, very interesting.
Very interesting. Very interesting stuff.
It's
Randall.
elementary, my dear Watson.
Well, and somewhat complicated, and maybe a clue to why it gets ignored in these other models.
Well, sure.
So much potential variability. Is like, okay, how do we put this into a model? Let's just ignore it and say it's steady state.
Mm-hmm. Well, I mean, for most of the 20th century, the idea was expressed in the term solar constant. And when all of this global warming stuff really began in the late 80s and early 90s, we were just then at the very beginning of satellite observations of the sun. So, I mean, we've come an enormously long ways in the last 25 years. And the problem is that the entrenched political agenda on the whole climate change narrative was already in place, and it didn't have a place. There was no area in that model for the role of the sun. It was the solar constant. Well, because the sun's changes are so insignificant, we don't need to complicate our models by including the sun. That's basically what it was. And now, of course, the narrative has become so entrenched, and this is why they're going after solar physicists and solar scientists, which is happening right now. You should see the backlash against this latest paper by Willie Soon and his colleagues, who are some of the foremost solar physicists and solar scientists on Earth. And they are being viciously attacked in a smear. It's a disgusting smear campaign, but that's happening just like it is right across the spectrum. You know, it's the same mindset that attacked Graham Hancock on Ancient Apocalypse. You would think, really, it's just a speculative documentary program about unanswered questions about our own past would be, promoting conspiracy theories and white supremacism and racism. It's and what's happening to the Comet Research Group, who are finding it impossible to get their papers published and their research published. But the truth will prevail. In the end, I'm totally confident that.
And I've said before, the truth resonates, and people feel that vibration. Things just feel true. You get it, right?
Mm-hmm.
People can sense that at a deeper level.
Yeah, and people who haven't become totally zombified by drinking the Kool-Aid.
Yeah.
You know where that term comes from, Kyle, drinking the Kool-Aid?
Nope. I don't think I know where it comes from.
Back in
hear the whole story.
I bet you that Mike probably knows.
Jim Jones, Guyana.
Yeah, Jim Jones. Yeah.
Yeah, Jim Jones. Over 900 people drank cyanide-laced Kool-Aid. And over I would say there was over 300 of those 900 people were infants and kids. And so the grown-ups gave them the Kool-Aid, and then the grown-ups drank the Kool-Aid. And you had 900 people. And you got to ask, how is such a thing possible?
And a congressman went down there to
Leo Ryan. Yeah.
To investigate, and they shot him.
They sure did. And it was after they shot him that
they all committed suicide. But the issue is, how do people get that far gone?
They committed murder and then suicide.
That's right.
Yeah. Well, this is what happens when you take indoctrination brainwashing to its final conclusion.
Yeah, I meant mass murder. They fed the kids Kool-Aid. Yeah.
Yeah, it was a horrible thing. But so, it's not to that level, but you've got a lot of people who are thoroughly brainwashed, and you've got a growing number of people who I think are waking up and asking questions. And the key is, I think and now I'm going to include you guys, Kyle and Russ. Certainly Brad is getting up in years. I would be considered an elder. You guys are getting to, Russ, you're not officially middle-aged yet.
Yeah, I am.
Oh yeah.
You are.
Sure. Yeah.
So you guys are getting in the middle.
40.
Middle ages, like
40.
Shit.
Well, that's what it was.
We're middle aged. We're in the 1200s.
Yeah, I'm medieval, bro.
Yeah.
But I think, this is why it's so important to get an alternative narrative out. And too many young people are growing up having been spoon-fed this bullshit since the 90s is when it all really began in earnest. The acceleration, the takeover of the education system and academic systems, the takeover of the media, the indoctrination of young people and stuff into the global warming
Gore's
nonsense.
Earth in the Balance was mid-90s.
Yep. So now what we have is they've come of age. They're now of college age and, late teens, early 20s, mid-20s. And you can see, they're the ones out there gluing their hands to interstates. You got to be pretty far gone to do that. And to think that what you're doing is somehow accomplishing anything besides turning people off, going out and blockading roads and getting a bunch of motorists extremely pissed off. That's not helping their cause. But here's the thing. None of them, if you were to isolate any one of them from the herd and from their echo chamber and actually try to talk to them rationally about the science of climate change, what you would quickly learn is they know absolutely nothing about the science at all. Completely unfamiliar with any of the stuff we're talking about tonight, any of the stuff we've talked about for the last year or two on this podcast relative to climate change, relative to global change. How is it that they've come through, 12 to 15, 16 years of the education system and they don't know any of this? Well, it's got to be by design.
Well, it's like a whole army of Manchurian candidates.
Yep.
Right. There's been a brainwashing, and that's just they take these signals and make these silly acts that's totally not of their own volition.
But like you said, Brad, the truth resonates.
Yeah.
And I think there's a lot we're seeing the younger people showing up on our tours, knowing that there's a much more interesting and true story out there, an alternate story, that it's not all settled. It's not all figured out. And you just have to go along with the consensus and live the way we tell you to live.
Well, and your presentation of it definitely invites a broad spectrum of people, because you're clear and you're thorough and you get to the basics and it's understandable. And I hear that consistently, that you're such an excellent teacher that they were just drawn in to listen more. And yeah, kudos to you for having those skills to spread that truth that does resonate and people tune into.
I think it's two things, neither of which is necessarily feeding my ego about all this, but one is obsessive curiosity and interest. So ongoing studies and research and learning since I was a teenager. Okay, that's one thing. And then, 30 years of presenting this information to people in varying capacities, you essentially learn that there's a way of communicating, a way of organizing your information, and a way of presenting it to people that they respond to. And the idea is you don't want to talk over somebody's head so they walk away from a lecture or presentation with very little retention and not knowing what you even talked about.
What'd that guy say?
The challenge and the art of it is figuring out, first of all, mastery of the material, which there's, of course, many degrees when you get into some of these complicated subjects. But, I don't claim final knowledge about any of this stuff. It's just that in terms of the study that I've done, the research that I've done, there's probably, a diminishing number of people that have devoted over half a century to in-depth, intense studies of this kind of information. So I did that. I still do that. I'm still as curious now about stuff as I was 50 years ago. Absolutely. In the interim, I've learned a lot, and I think it really comes down to really knowing the right questions to ask. I think that's ultimately what it's about.
That's it right there.
Mm-hmm.
I agree with that.
Well, yeah, it's a good point to wrap up on. We're pretty close to that time.
Yep. RandallCarlson.com.
Shedding light on the sun. That's the title of the episode.
There you go. That's a perfect title.
Well, I thought we covered some good territory tonight.
Oh, yeah.
Yes, we did.
I really enjoyed it.
Yeah. This is a great show, guys.
Yeah. Me too.
Thanks, Randall.
Oh, you got it. Yep. Thank you, guys. Thanks, Mike, Brad, Russ, and Kyle.
Aye.
Right.
Thanks, everybody out there.
Appreciate everybody. Yeah. See us on Patreon. Good night.